Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the linear algebra guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Okay, so before learning how to solve a system of equations using Gaussian elimination, we need to learn what three elementary operations that we can apply so that we can somehow simplify the system of equations in the form of a matrix in a way that makes the solution easier to see. And that's essentially the essence of what we're doing here. We're taking our matrix and we're converting it to a form where the solutions are easier to see, but at the same time the solutions are still preserved. So we can apply these three operations so that we can change the matrix in some way but still preserve its solutions. So the first elementary operation that does this is switching two rows. If we were to switch two rows of a matrix, we'd change the matrix in some way, the system of equations, but we'd still have the same solution. And that makes sense because let's say we were to switch equation 1 and equation 2 in a three equation system. Well, we're just switching the two equations, which is equivalent to switching rows. We're not really changing the solution by doing that. So it's just a different way of representing the same system. So it makes sense that we can do this and still preserve the solution. And the way we represent this, and you need to know these by the way, because you need to effectively communicate this to whoever's reading your work, probably your teacher. So this is how you communicate switching two rows. We write row one. I'm going to just switch row 1 and row 2. We can write row 1 and draw a two-way arrow between row 1 and row 2, and this represents that I'm switching the first two rows of our matrix. So let's just show what that looks like. So row 2 would become row 1 in our new matrix. So 0, 4, 5, 8. Row 1 would become row 2 in our new matrix. So 1, 2, 3, 7. And since we're only switching row 1 and row 2, row 3 would just remain the same. Okay. So that's switching two rows. Another elementary operation that we can do that preserves a solution is multiplying an entire row by a non-zero constant. For example, let's multiply the first row of this matrix by 2. To do that, we say 2 times row 1 to show that we're multiplying the first row of this matrix by 2, and draw an arrow that points to row 1, and this signifies that we're affecting row 1 in our final matrix. We're taking row 1 in our initial matrix, we're multiplying it by 2, and we're making that the new row in our final matrix, the new row 1 in our final matrix. So doing that would get us this matrix right here. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 7 is 14. I just went ahead and multiplied the entire first row by 2. You have to multiply every single term. Since this is only affecting the first row in our final matrix, the second and third row remain the same. So this would still be 0, 4, 5, 8, and this would still be 5, 6, 7, 9. The last elementary operation that we can apply is adding or subtracting a multiple of another row. Doing this still would give us a system with the exact same solutions. I'll show you what this means. So basically, if we were to take row 2 and add twice row 1 to it, we would obtain a new matrix but with the same solutions. You would represent adding twice row 1 to row 2 like this. Row 2 plus 2 row 1, and we would change row 2 because we're adding a multiple of another row, in this case row 1. What we can't do is say 2 row 2 plus row 1 and still change row 2. The reason we can't do this, but we can do the other one, is because this right here isn't an elementary operation. I can draw a better X than that. There you go. That right there isn't an elementary operation because we're not adding a multiple of another row. We're multiplying the same row by something and then adding it to another row. We're technically doing the second elementary operation and the third elementary operation at the same time, which is incorrect. We can only do one elementary operation at a time. That's why they're elementary. Although it's technically legal, I don't encourage you in doing it because once again, you should probably do it step by step in a way that makes it much easier to see for your teacher. So we can add or subtract a multiple of another row in the like this right here. This is an example of what you can do. Row 2 plus twice row 1, and we're changing row 2. Let me show you how that actually looks like. So since we're only changing row 2 in our final matrix, even though we do have like row 1 written here, we don't do anything with row 1. We're only going to change row 2 in our final matrix. So row 1 will remain exactly the same. We leave it just as it is. Cool. Now row 2 will change because we're changing row 2. So we have to add twice of every term in row 1 to every term in row 2. That means that 0 plus 2 times 1, which is 2, because I'm multiplying row 1 by 2, 4 times 2 times 2, which is 4 plus 4, which is 8, 5 plus 2 times 3, which is 5 plus 6, which is 11, and 8 plus 2 times 7, which is 8 plus 14, which is 22. I just went ahead and added twice the term on the first row to the term on the second row. And that's exactly what this elementary operation does. Since we're only affecting row 2 in our final matrix, row 3 will remain exactly the same. So we will still have 5, 6, 7, and 9 in row 3 because we're only changing row 2. And the same applies to row 1. Okay, those are 3 elementary operations. Now let's see how we can apply this to an actual system of equations and solve it. Over here, I have an example of such a system. So let's try applying our 3 elementary operations and reduce this system to a form where its solution is easier to see. The first step is just to represent the system in the form of a matrix, so we can actually apply the operations that we learned. So let's do that. Here, you should be good with this already, because that's what we did in the previous segment. But basically, this column represents x. This column will represent the coefficients of y. So 1, 2, 1. This column would represent the coefficients of z. So 2, minus 1, and 2. And we add on the column that represents what each of these equations are equal to. So 2x plus y plus 2z is equal to negative 2. Negative 2x plus 2y minus z is equal to negative 5. And 4x plus y plus 2z, plus 2z is equal to 0. Okay, this is the matrix that we need to manipulate. And in order to manipulate this system and obtain 3 solutions, we need to create 3 leading ones. So a leading one is essentially a one that is the first occurring non-zero term in a row. So we need to make 3 terms in this matrix leading ones, and those terms should exist across the main diagonal. I will show you what I mean in a second, but before you solve any system, what I want you to do is when you're at this matrix, I want you to circle the terms that you want to make leading ones. It will make your life a lot easier because you'll see exactly which terms you need to make leading ones. So remember, the leading ones are across the main diagonal. So from top left to bottom right. So this term right here, this term right here, and this term right here. We need to make, and coincidentally they're all 2's. That isn't obvious. That isn't always the case, but here it is. We need to make all these 2's into leading ones. And we do that by making them by making them ones and then making them the first non-zero terms in their row. I'll show you what I mean. So for the first leading one, it's kind of simple because it's already the first term in the row, so we don't have to eliminate any terms before it. So we can just divide the first row by 2. Let's do that. So if we divide the first row by 2, doing that would get us the first leading one, because it's the first non-zero term in the row, which is easy to create because it's the first term in the row. So this is our first leading one. 2 divided by 2 is 1. 1 divided by 2 is 1 over 2. 2 divided by 2 is 1. Negative 2 divided by 2 is negative 1. And the second row, since we're only affecting the first row in our matrix, the second row remains the same. And the same applies to the third row, since we're only affecting the first row. Okay, so that is how we that is the first step. That's how we create our first leading one. Now we need to create our second leading one. And in order to do that, we need to first eliminate any terms that come before it, because it has to be the first non-zero term in this matrix. So in other words, we need to eliminate this negative 2. Because to make it the first non-zero term in this matrix, we need to make any terms that come before it equal to 0. So how do we eliminate this negative 2? Well, we can't really divide. We can't make negative 2 0 by dividing it by anything. You can't divide a number by anything and make it 0. So we need to use another operation. Similarly, since we can't divide by anything and make it 0, we can't really switch a row with it to make it 0, because none of the other rows have a 0 here. So what we need to do is we need to add a multiple of another row. That's the only operation that we have left. Now, this is where a few students get a little bit tripped up, because it's sometimes it's presented as unclear on why they do this. So I'll try and simplify it for you. Basically, of course, we need to add a multiple of another row, and there's multiple ways that we can eliminate the negative 2. But the way that I like to do it is use the row with the leading one in this column. What I mean by that is here we have a negative 2. So go up and down this column and see which row has a leading 1 in it. The first row has a leading 1 in it. So we need to use the first row to eliminate the second row. Now, to use the first row to eliminate the second row, since we have a 1 here, how do we use a 1? How do we use a multiple of a 1 to eliminate a negative 2? Well, if we multiply the 1 by 2 and add it to the negative 2, then that 2 becomes 0. So that's what we need to do. We need to take 2 times the first row and add it to the second row, because 2 times 1 plus negative 2 equals 0. I'll just show you what I did there once again, because it's really important. Here, I see that I need to eliminate this negative 2. So to do that, I go up and down this column and I find the leading one. I found a leading one in the first row. So how do I use a 1 to eliminate a negative 2? Well, I can add 2 times 1 to negative 2, and that will make this negative 2 a 0. So I need to add 2 times row 1 to row 2. So that's the elementary operation I need to apply here. So now let's do that. Row 2 plus 2 times row 1, and since we're trying to eliminate negative 2, we want to change row 2. So that's an easier way of looking at it. It's not the only way you can solve the system, and sometimes there might be easier ways you could do it, but I like to just stick to one method and use that, and this is relatively simple. So yeah, but you can, if there's another method that you find easier, or you find a way to solve a system that's easier, as long as you eliminate the negative 2 and you create the correct number of leading ones, you're still going to arrive at the same solution. So here, since we're only affecting row 2, row 1 will stay the same. Sorry about that. So row 1 will stay the exact same. We won't have any difference here. Okay, so now row 2 though will change. Just like we want, negative 2 plus 2 is 0. 2 plus 2 over 2, which is 2 plus 1 is 3. And 1 plus 2 is also 3. Oh, sorry, this is a negative 1. My bad. Okay, yeah, that makes sense. So negative 1 plus 2 is positive 1. And negative 5 minus 3, or minus 2 rather, is minus 7. So negative 2 plus 2 is 0, 2 plus 1 is 3, negative 1 plus 2 is 1, and negative 5 minus 2 is negative 7. And since we're only affecting row 2, row 3 remains the same. Okay, now we can move on to create our second leading one. To create our second leading one, which is this one over here, we can take this entire row and divide it by 3, because dividing this 3 by 3 will give us a 1. So that's what we do. It's very procedural and it's systematic. This method is systematic once you understand it, but it's just getting that initial understanding that's important. So here, since we want to make the 3 a 1, we have to divide the entire row by a 3. So let's do that. 1 over 3, row 2, and we want to replace row 2 in our final matrix. Okay, so the first row remains the same. The second row, well, 0 over 3 is just 0. 3 over 3 is 1. 1 over 3 is 1, well, 1 over 3. Negative 7 over 3 is again negative 7 over 3. And 4, 1, 2, 0, since we're only affecting row 2, this row will remain the same. So we'll still have 4, 1, 2, and 0. Okay, now we move on to the last row. In the last row, to create our last leading one, we need this term to become our last leading one, this 2 over here. But to do that, we need to eliminate any non-zero terms that come before it. So we need to eliminate this 4. We need to eliminate this 1. So to do that, we can use my trick again, where we go up the column and find the leading one. So let's do that. Here, we go to column 1. The first entry, which is in column 1. We go here, we want to eliminate this 4. So we go up this column and we look for the leading one. We see this leading one over here. So we can use this leading one to eliminate this 4. But how do we use this leading one to eliminate a 4? Well, we can multiply it by minus 4, because 4 minus 4 is 0. So we have to add minus 4 times the first row to the third row to eliminate this 4. How do I know that? Well, I see that this 4 is in this column, and I need to use this leading one to do that. And since this leading one is in the first row, I need to add minus 4 times the first row to the third row in order to eliminate this 4. So let's do that. Row 3 minus 4 times row 1, and we want to change row 3 in our final matrix, because that's where the term we want to eliminate is. So the first row will remain the same, because we are only affecting the third row in our final matrix. The second row will once again remain the same. Now, the third row is what will change. 4 minus 4 is 0. 1 minus 4 over 2, that's minus 1, because that's 1 minus 2. 2 minus 4 is minus 2. And 0 plus 4 is positive 4. Okay, so we've eliminated the first non-zero term. Now we need to eliminate the second non-zero term. So let's go ahead and let's eliminate this term like I taught you to do. So we see there's a minus 1 here. We need to find the row with a leading 1 here. Well, we go up and we see that the second row has a leading 1 here. So we need to use the second row to eliminate the third row. But how do we use a 1 to a minus 1? How do we use a 1 to eliminate a minus 1? Well, 1 minus 1 is 0, so we can just add the second row and the third row. So let's do that. Row 3 plus row 2, and we're going to change row 3. We're changing row 3 because that's where we want to eliminate the term. Okay. So the first row will remain the same. The second row will once again remain the same. Now the third row will change. 0 plus 0, because we're adding the two rows, I'm adding 0 and 0, which is still 0. Minus 1 plus 1, just like we want, is 0. Minus 2 plus 1/3 is minus 5/3. And 4 minus 7/3 is 5/3. We're almost done. Now the last step is to make to create the last leading one, and to do that, how do we make a minus 5/3 into a 1? Well, we multiply by minus 3/5. So we multiply the entire last row by minus 3/5 to make the last leading one. 1. So these two rows will remain the same because we're only affecting the last row of our final matrix. We will have 0, 0, 1 to create the last leading one, just like we wanted. And minus 3/5 times 5/3 is minus 1. Okay, so the hard part is over, I assure you. The hardest part of this entire process, especially for students who are learning this method for the first time, is just being able to identify how you can add a multiple of one row to another to eliminate a specific term. Once you get that down, this entire method is simple. Creating the leading one, once you eliminate all the non-zero terms before it, is just dividing the entire row by a number. That's really easy, like anyone can do it. But it's just making sure you understand how you can eliminate specific terms. And I tried to make that easier for you by using my trick of going up, finding the row that has a leading one, and knowing that you have to do something with that row. Now let's go ahead and finish solving the system. So this column right here contains the coefficients of the variable x. This column right here contains the coefficients of the variable y, and this column right here contains the coefficients of the variable z. And this right here contains what each equation is equal to. So we always start writing from bottom up. So here we know that, well, 1z is equal to minus 1. So z is just equal to minus 1. That's our solution for the variable z. The next column, we can say that y plus 1/3 z is equal to minus 7/3. If you substitute in the fact that z is equal to minus 1, you can rearrange this equation to find that y is equal to minus 2. For the last equation, we know that x plus 1/2 y plus z is equal to minus 1. We know that z is minus 1, I know that y is minus 2, so we get x minus 1 is equal to minus 1. So x is equal to 1. And these are the solutions to this system of equation. Okay, so one last thing before I end the video, or end the segment rather, is that you need to realize that this specific form of a matrix has a name. We call this row echelon form. Now, the reason that it's important that you know this name is there's multiple forms that you can reduce a matrix to, and this is one of them. And the forms that you often reduce a matrix to make the solutions easier to see. So here we reduce the matrix to row echelon form. And the reason that this is row echelon form is we created as many leading ones as possible. So if you just look here at our final matrix, we have a leading one here, we have a leading one here, and we have a leading one here. We have leading ones along the main diagonal. Now notice how I said we created as many leading ones here as possible. Here we were able to successfully create all 3 leading ones. But in the next few segments, you'll see that that isn't always the case. This was a very nice problem because we arrived at 3 perfect solutions to each variable. We know exactly what each variable is equal to, and that's the only set of variables that can actually solve the system. That isn't always the case. There are cases that I already described that have either infinite or no solutions, and we're going to go over how we can identify those cases and what we can do with those in the next segment. But it's important for now that you realize that this matrix is in row echelon form, where we created as many leading ones as possible. We can further reduce this matrix into something called row reduced echelon form, but I'll go over that in a future segment as well. Finally, you can check your solutions, if this is on an examination or homework or whatever, by just taking these numbers and substituting them back into our original equations. So if we substituted in z is equal to minus 1, y is equal to negative 2, x is equal to 1, we would find that these solutions satisfy each and every one of these 3 equations. So that's how you know that what you did was correct, and that's the way you can verify your solution.